So I'm about to go live. You ready?
Yeah.
Cool. I of course forgot to go to the start screen, but it's been a while. So hi, how's it going, everybody? It's been a while since we live streamed. It's been crazy. I mean, like OBS has been really not cooperating with me lately, which is very sad. Hence, very few videos and very few live streams. If you knew how many times this next upcoming tutorial I shot it and then in post realized that it's like laggy and weird and it's so stressful, and then when I'm doing the thing I'm stressing about it, so I'm not like explaining the shit correctly. So it's been a shit show, so sorry or whatever. I don't think anybody cares too much. And hi, Leandro, how are you?
Hello. I am good, and I think that you need to do what I did in my videos like 1.5 years ago, something like that. I was doing a video about some workflows in OBS and ReaFIR, and the only way technically I could record the videos because I was talking about OBS and ReaFIR, and I would use OBS and ReaFIR to record. I was doing kind of a meta video. I just put my iPhone pointed at my computer, and then that was my screen capture. So I think you need to resort to that area. It's the end of the world for you.
Like, my phone is a piece of shit too. I've been trying like QuickTime, and that's been really horrible because QuickTime, as the time that you shoot goes up, because it feels like it doesn't save the video because you save it at the end, right? So when you do longer videos, first of all, like 9 times out of 10, I just get the wheel and I'm like, fuck. And the other 1 time out of 10, like after a certain amount of length, it starts lagging because I guess it's like not writing to a hard disk. It's keeping all the data. So I have to stop all the time. It's really just been killing my workflow, and like I don't know. I'm not a fan of compromises. My videos are shit as they are, and now I'm doing them at like 2% capacity and stopping all the time. Then I gotta match the thing. Ugh, it's been so goddamn annoying. And in fact, I think I'm gonna do like a video essay next, so I don't have to do a capture. I'm just gonna talk about EQs. So the channel's pivoting, and it's not because I want to pivot, but it's because OBS just forced my hand.
Embrace your limitations.
Yeah, exactly. So I guess I don't know. We'll see. We'll see if people hate it. I guess then I'll just stop making videos forever. How is how is stuff with you, Leandro?
Well, I've been looking at computers that are relatively small because it's not that I don't have the space on my desk, but I don't like having a lot of junk around. And it seems like for a streaming computer, it only needs a relatively okay CPU. An i5 is good enough. Probably, maybe an i7. You definitely don't need an i9. And you don't need any sort of GPU because the streaming computer is mostly doing CPU stuff to encode the stream and to encode the recording of the video we are doing. So it can be a relatively inexpensive computer. Probably we can get away with it like a $300, $500 PC. Definitely not a Mac. So yeah, I've been looking into that. I may bite the bullet and buy one of those, and then I'll let you know if it's worth the investment, because it's not too much. But then again,
So
it's more work to set everything up and keep it up to date, and then debug and.
So out of your Mac Mini, you would take an HDMI out, which do they even have those? Like you would send HDMI, capture card, USB, and then webcam would be on the second computer, right? Is that the game plan?
No, I probably would be using NDI.
Oh, NDI,
to send. Yeah, I would be running OBS on the computer that I'm using to do this stuff.
Yeah.
The computer whose screen is being captured. So I would run OBS on that computer, but I would turn off preview, and I would I would have a single scene with a single source, which is the computer screen, and I would send that over the network using NDI, everything cabled, everything wired, and then on the second computer, the streaming computer or the recording computer, would be running OBS too, and it would be only running OBS. The only thing that runs on that machine is OBS. And it would be a PC because it's much cheaper, and because it's always nice to have a PC around when you need to test stuff or whatever the case may be. When you want to like try out something that may break your ReaFIR installation, you can always do it on Windows, whatever. The second computer is just running OBS, capturing the video from the camera.
Yeah.
Using the capture card as usual, microphone connected to that computer, and via NDI getting the source of the computer screen and audio from that computer.
Without having any data to back this up, I'm just like, there's no way NDI will work seamlessly. But I will wait for...
I used that before. I had a second computer and I was doing exactly that. It worked super well.
I mean, like OBS works super well for everybody on the planet except me. So I just...
No, that's hardly true. Everyone complains about OBS. And it's not OBS's fault. It's just that this is a freaking difficult thing to do.
Yeah,
Previously, before YouTube and streaming, people needed TV network stations to do the kind of thing the kind of broadcast we are doing from our bedrooms. So it is a complicated task and it's demanding on the computer, and NDI works remarkably well. And they updated, now they have like version 5, which has even cooler features. So I don't expect that part of the equation would be the problem. The problem is just that it would take me hours to wire everything and make sense of the routing and installing all the 5 different black holes I would need to do the mix minus for the gas. And it's just a lot of work. But I am very confident that the setup will work as long as the computer is up to the task. So the thing is, you have to get the second computer that you want to be cheaper than your primary computer, because it will be only running OBS for the stream. But if you go too cheap, then you have to like go back to the store and change pieces. That's so fun.
Even the stream seems to be doing okay. So really, like, my personal issue is really just recording 2K. But yeah, I'll let you be the lab rat on that. Bo is here and says hi. Hey, Bo.
Hello, Bo.
I've been mixing our song, which is another thing that I was doing on live streams and having lots of fun doing it and learning a lot. And now, like, if OBS is open and my mix is open, everything lags. And I can, like, start freezing stuff. But then... like already it takes me like 4 times as long when I mix on a live stream because I'm like chatting to people and then having to like freeze and unfreeze stuff. So that's no longer happening. Thanks, Obama. Yeah, this is more like a therapy session than JSFX coding live stream. But now that we have Bo here, why don't I switch to this other scene where we are considerably smaller, and I'll put you underneath there and I'll make us a little bigger so that we cover the thing that's doing the other thing. All right. And yeah, it's been a while since we had a JSFX coding stream because you're helping me with the website on your channel. So this is literally where we left off the last project with this rotation thing, which I like. Yeah, I remember what we were doing, but we didn't like fully implement it. But I don't know, like if you want to just kind of pick up where we left off, or if you want to start something new.
I'll let you decide, and Bo can vote as well, and anyone else who is watching. If you want to continue doing this, we are in a good position to continue doing this because we have, I think, figured all the hard parts. And I don't think we are near the finish line, but we figured lots of hard parts.
Yeah.
So that could be fun. But we can always do Lua. You mentioned last week that you wanted to do some Lua because we haven't done that in even longer.
Yeah.
So Lua is always fun.
Yeah, Lua is fun. I mean, at least from like a selfish point of view, I feel like I can get somewhat far with Lua, and with JSFX I'm like I would never be able to like reinvent anything. I'd just be able to do something like semi fun. But yeah, we did
It's
the
interesting that you say that because conceptually, JSFX is a simpler language than Lua. It has fewer features. In Lua, there are different flavors of functions. There are the anonymous functions that we talked about once, and Lua patterns, which is
that stuff has
present
hard.
in JSFX, but we tend not to worry about strings too much until you get to the user interface, but we haven't really considered
Yeah.
that. Like we don't have labels and complicated stuff there. So Lua is a richer language. For one thing, it has like proper strings and Boolean values and all that stuff. And JSFX is just a bunch of numbers. But I guess the mathematics behind the kinds of things you would need to do in JSFX is a bit more complicated. So yeah.
Maybe it also speaks to my amateurness that I'm like, oh, I feel like I have a decent grasp of Lua, and it's like there's so much, especially with patterns and stuff. Like when you make a pattern and explain it to me, I get it. But then if I have to make my own pattern, like I'll probably not be able to pull it off.
Yeah, it's a lifelong journey.
Yeah.
There is always more depth to that. Lua patterns not so much, but regular expressions are so rich. And there is a whole field of research on how you can use regular expression for different tasks. And if you just go a little bit beyond the regular expressions, or even some flavors of regular expressions in some languages have these features where you can do the thing that is right beyond a regular language, something called a context-free language, then your universe really opens up to the kinds of pattern matching that you can do. And that's how people parse programming languages, for instance, using context-free grammars. And yeah, I could talk about this all day because I have spent 6 years doing a PhD in programming language theory, which involved parsing and all that stuff quite a bit. So yeah, but let's not do that. Let's Lua is a fine language because you can sort of learn the whole language in a week if you set yourself up to that. You can read the Lua programming, the programming in Lua book, and you have a pretty good grasp of everything that Lua can do. And then of course you have to use extensions and you have to learn the ReaFIR API, but like the core language fits in your brain, which is, I think, a nice thing.
Yeah.
It's definitely not true of C++.
Yeah. So Bo is voting for finishing the ping pong. So cool. Well, let's just do that. Bo is our basically tiebreaker, I guess, here. But I guess now that you brought up C++, maybe you want to tell everybody about the study group as well.
Yeah, sure. So tomorrow at 6:30 UTC, we will be having our second meeting of the C++ Digital Signal Processing JUICE study group, where we are taking people who are like absolutely new to this area, and some people who know C++ fairly well, people who have written books about C++, but may not necessarily know too much about digital signal processing and programming for audio. So diverse group, lots of fun people, and people are engaging in the Discord channel. You can go to the unofficial ReaFIR Discord server, the unofficial user group for ReaFIR. And there is a channel under my name, Leandro over there, and we are hanging out there. And people have like different interests. Some people are exploring like low-level build systems, and some people are looking into different kinds of APIs to build audio plugins. And yeah, tomorrow the plan is to see what people did over the course of 2 weeks, and there probably will be lots of questions. Some people will have developed a complete proof of concept plugin, and some people will be like, how do I even get this to compile?
Yeah. That's me.
Yeah, we'll sort through the So how far along are you?
I
not to.
read the chapter, but
Oh, great.
in terms of setting up C++ in any of the ways mentioned, I just didn't have time to do it. And yeah, haven't done it yet. I don't think I'll have time today either.
Yeah, so the first chapter that Arya mentioned is this book that we are sort of loosely following along. And the first chapter is pretty much about, if you are here watching this stream, you probably know how to get through that chapter, because it deals with concepts like the Nyquist frequency and sampling rates and that sort of stuff. So it's pretty basic, but we need to establish a language to have some sorts of conversations. So I thought for this first 2 weeks, we would just like see what the space even is, and talk about the basics. And when I say basics, it seems like stuff that maybe everyone should know, but that's far from being true. This is stuff like that I have been learning this past few months, and it's pretty complicated, very mathematical.
Yeah.
But together we'll power through, we'll make it. It will be a lot of fun. So tomorrow we are meeting again, sharing what we learned and establishing our goals. Like, what do you want to do in terms of creating a plugin? What is the plugin you want to create, or what is the algorithm that you want to learn about? So that's what we are doing tomorrow.
Yeah, I'm looking forward to it. All right, so I guess in that sense, like, it makes me really appreciate JSFX, because like, there we go, I can just write JSFX, boom, now I'm writing JSFX. So good job, Justin Frankel.
Yeah.
All right, it's been a while since I did the window resizing. I always try to keep everything in view. So I guess I'll do a little bit of this, and maybe I'll float this. And I'll do a little bit of this. I'll make it small. I'll make this big. This is the wrong thing to make big. I'll make this big. So the rotation thing, yeah, we were just kind of like hashing out the like basics of drawing a curved line and stuff. So I think we did that. We got what we wanted out of that, where we rotated a line basically. So yes.
Yeah, so I think there are, well, many things. We have a big list of things to do over there on the top of the file, but we can work on the audio portion of the thing, or we can work on the graphical user interface. We can flesh out the whole drawing of the waveforms following a path.
So I think you drew the waveform, right? We did that bit.
Well, we didn't do it on your plugin, but on my stream and in this library, there is some code that can draw waveforms. Now, the library is still under development, so many things changed since you started using it. And if you just update to the latest version, everything will break.
Okay.
So I guess we'll just, maybe if we want to do the waveforms, if that's what we decide to do, we can do some other stuff on the list. Like we can add a bit crusher to the delay path. Just have fun with audio stuff too.
But yeah, bit crushing sounds easy too. That, yeah, it sounds like math,
so
right?
You can do saturation on the delay path. There are many things that we can do on the delay path. Like we can do the bit crushing and the saturation are probably the low-hanging fruits. And high pass on low pass is also relatively straightforward because we have implemented that. But we could just quickly re-implement SVF filters together. I don't think it's part of the version of the library that you have right now, but it's such a simple thing to hash out the code for. So we can do some stuff with audio on the delay path, or we can do the drawing or anything else you have in mind.
Quick question on that. So if I update your library, like some stuff will break. But if I download a new version of your library under a new name and then import it up here, would that be a thing?
Then
or that
it's actually an interesting question. I think, I don't know, I haven't tested. But the main concern is functions with the same names but different implementations, right? If two functions have the same name but they do different things, which is pretty much the case these days. I probably renamed like underscore memory underscore memory dot new. No, that second line on the init block, that changed. And I think that the imports are considered in order. So if you take the new version of the library and you put it above, the old version will overwrite any functions with the same name. But I have never tested this, so I don't know what the behavior is there.
Bo says your audio is a bit low, but like on my meters, they are like both right at around -3 dB. So I don't know what's going on, Bo. I guess let me listen to it. I guess I sound much louder, so I can turn myself down. Leandro seems pretty good. So I guess let us know if that helped. I brought myself down a couple of dBs.
Okay. On my side, I am like around -3 to -6 because I have my whole audio chain. So it should be at -19 LUFS.
Yeah, same here. In fact, as I turn myself down, now on the meters, I'm reading a little lower than you, but I think it's okay. Hopefully it's okay, but if it's like really fucky, I guess let us know. All right, so I guess so I guess doing a new library that may kind of complicate things. I say let's do maybe, well, the FFT blurring, that may be a big undertaking, but maybe we can do a little bit of saturation and bit crushing.
Yeah, absolutely. Yeah. Let's do that.
Okay.
So first task, let's find where in the code is our, so I guess what we are talking about is we have a dry signal and a wet signal. The dry signal we don't want to touch. We don't want to bit crush the dry signal. Sorry, the dry signal we don't want to bit crush. We want to put the bit crusher on the delay path. So we take the audio and we are going to store it in a circular buffer so that we can replay it later. So before it gets into the circular buffer, that's where we put the bit crusher, right?
Oh, I see. I guess the way I was seeing it is like we get into the buffer and then we trigger the saturation. But you're saying like even before the audio gets in, but after the dry signal is received.
Well,
and I guess those are different results, right? So if the saturation is inside the buffer somehow, then at each repeat of the delay gets more saturated versus applying an overall amount of, because to me, like if the saturation is going before the buffer, like why not just use another effects and like do a parallel processing like in ReaFIR, you know what I mean? Like what feature are we adding to the thing?
Yeah, so the thing to keep in mind is that our plugin, our delay, is unusual in the sense that it has no feedback. We have a bunch of taps. We have no feedback, which is kind of unusual, but we have way more taps than a typical delay. What we have, like 100 taps, something like that.
Yeah, I think so.
I forget.
It's somewhere here.
So the thing is, you take the sample and you're gonna put it as it is. We take the sample, we put it in the delay, in the circular buffer, and then we take it out and replay it at a later point. But we never put it back
into
there's
itself.
No feedback. There's no. Yeah. So it doesn't really matter from a sonic perspective. It does not matter if you are going to do all the processing, the bit crushing, saturation, whatever you want to do, filtering. It doesn't matter if you do it before you put it in the buffer or after you take it out but before playing it back. It doesn't matter because it's going to be at the same audio. It's not going to feedback, so it doesn't really matter. The difference is in performance. If you do it right before putting it in the buffer, we can just play it back. So we are going to process a sample once. But if you decide to put the sample in the buffer as it is and do all the processing, like the bit crushing on the way out before reproduction, you will have to bit crush that sample over and over as the multiple taps replay that. So from a performance perspective, it's smarter to do the processing before putting stuff on the circular buffer. From a sonic perspective, it does not matter.
So I guess thinking about this, like since we don't have a feedback, since we're not feeding the thing back into itself, in my mind, it's actually totally useless to implement like saturation or bit crushing or anything like that, because you would get the same results just putting that effect before or after the delay, right?
Yeah, so that's, I guess, the second part of this. For me, there are two reasons to implement saturation, bit crushing, filters, and so forth. The first is because it's cool. It would be nice to talk about how to do saturation, a very simple one, and how to do bit crushing, very simple. So that could be entertaining and educational. The second reason is convenience. If you have something that you can just drop on the track and then you can play around with a bunch of cool little effects, you can get some nice results, maybe faster, and maybe results that you would not get otherwise because you would be playing with routing and creating tracks and moving things around. And then you think, no, it's probably not going to sound good. Let me move on and do something else. So it's always a trade-off, right? We are going to make our plugin slightly more complicated, but we'll also make it more powerful. And ultimately, why would you need bit crushing or saturation anywhere in any plugin? You can always route things weirdly in ReaFIR to get what you want, like that trick that I learned of doing multiple tracks and feeding them into each other so that you can put any effect on the delay path. So if you want to do that thing, it's like the thing that we are doing on Wednesdays where we are doing synthesizers, sort of using ReaFIR as a big modular synthesizer. You can. It's a trade-off in terms of like usability and
I think, okay, can I change my mind? Can we do pitch changes? That sounds crazy.
Yeah, sure.
Because Bo says bit crushers are a bit harsh, and I think bit crushers are very easy. So let's do like a medium difficulty, and high pass, low pass, I guess are cool, but we've already kind of done it. So maybe let's do pitch.
Saturation we didn't do.
No, we haven't done
it's also
that.
Fun.
Yeah.
But pitch changes, I have never done anything like that, but I do have an idea of how it should work.
Okay.
On a very naive level. So the reference that comes to mind to me is this tutorial that is on the Wiki. So have you been to the ReaFIR Wiki?
No.
Yeah, it exists,
Cool.
but it's very old.
I can also, like, if you want to drop a link, I guess drop it in Skype chat, and I'll share it with everybody in chat. But I'll go to the ReaFIR Wiki. ReaFIR.
Yeah, so
Wiki.
What you're looking for is... Give me a second.
Sure.
I am copying and pasting links around.
Text.
And this was my first introduction into JSFX. When I just learned that ReaFIR was a thing and JSFX was a thing, I started looking for references to learn it, and I came upon this. And it was written by a person whose plugins are part of the stock plugins in ReaFIR.
Yeah.
Many stock plugins by the author of this tutorial. Yeah, including a limiter that I know you are using in your chain for our stream right now. So we are using this person's plugins as we speak. So thank you, Michael, loser.
Yeah.
First for all your plugins, and second for all the knowledge and the inspiration too. So you can see that there is a section here, and these are very simple implementations of plugins. For instance, the limiter, I would just call a clipper.
Right.
The limiter that he implements there is just a hard clipper, which you could say is limiting, but it's kind of cheating.
Right.
But pitch shifting, there is a section on that as
Nice.
well. And the idea boils down to something super simple. We are going to do pitch shifting by changing the rate of playback. We have a delay line, right? And if you play the delay line one sample at a time, it's going to sound the same. But if you play it twice as fast, it's going to sound, well, twice as high. Yeah, an octave above. And if you want to play it more slowly, it will sound an octave below. So that's the theory. That's a very simple, kind of naive way of doing pitch shifting, but it works. And the biggest trick, the challenge here is that if you want to play things faster, you're going to run out of samples to play at some point, right? You capture 1,000 samples in your circular buffer, you play them half the time, but by the time you're done, you have only captured 500 more samples. So how do you deal with the 500 samples that you're missing? Well, the trick is you do two heads that are going to go over the circular buffer, and they're going to, like, for instance, play at double speed, and you're going to, as one is getting to the end of the buffer, the other one is right behind it, and you crossfade between the two. It's like a do you know the Shepard tone? It's like that for people.
Because there are also two types of, I guess, pitch shifting, which is one is like how you explained, like as a result of speed changing and all the frequencies like doubling in the case I mentioned. But there is another way, which is without changing the speed. And that is doing like what you're saying. But I guess you can do that like you can have two heads, or you can do it at like a granular level where you're maybe taking very small snippets of like 10 samples each and looping those, or 10 samples is too little, but like taking like a 1 millisecond or a 3 millisecond snippet of the audio and speeding that up and then just like duplicating it. Also, as we started talking about this, I kind of found it quite funny because the whole reason we made this delay was that, well, I could grab a normal delay or like an analog style delay, and I could automate its rate to get this ping pong effect, starting slow and getting fast. But I didn't want the pitch shift that happens as a result of that. So we made this, and now we're making a pitch shift on the thing whose point was that we don't have to.
But you know what? The thing that you are talking about and the thing that I am talking about are actually the same thing.
Right, it's just a number of like grains.
No, it's literally the same thing. Because if you think about the two playheads as I'm talking about, the way that they go through a section and then another one is going over another section to kind of cover the gaps. If you think about these two playheads as they are moving along, what they're doing is they're slicing the audio in small grains. Mm-hmm. So it is literally the same. It's just that the way you conceptualize it is you look at the big picture and you break it apart in smaller parts, and then you want to go over each one, while I am reasoning about it more from, I guess, an implementation perspective, where I know that if I overlap two of these grains, it's good enough. So I prefer to think in terms of the playhead. But yeah, thanks for bringing out this other interpretation, which is maybe more intuitive.
Yeah, that sounds like it could be fun. And I guess so. Okay, so you're saying the two playhead situation. And then if we... So the distance between these two playheads basically gives us the size of our slice, right?
Yes.
Okay. And then we can automate that. and then get an extra weirdness, I guess.
Yeah. Yeah, I think that makes sense. Right.
Cool.
So I guess what would be smart is first to try to make sense of pitch shifting and then incorporate it into the bigger plugin we are developing. Because this is all new stuff. For me, at least, it is. So I think that the thing we should do is try to work through this small tutorial, make sense of how it works, see what parameters we can change and if it sounds any good, and then we can bring it into, or maybe your homework can be to bring it into the bigger plugin. So yeah, I guess first things first, let's just try the naive thing. There is the full code below. Just copy, paste it into a new plugin, and let's run some audio through that and see what it sounds like.
Alright, I won't minimize this. I'll just go here. I'll minimize this. I'll make a new track. I'll close this. I'll open the FX browser. I'll go create new JSFX. Pit, shift, loser, test, and grab this baby, zoink, save it, recompiles okay. Already forgot what I called it, so Google loser, Google I said, what's happening? Okay. Pitch. Where's my pitch? Okay. Alright, whatever. It's here. Anyways. And a little bit of audio. I'll just add a ping pong. It's right here.
Can we have some, as a test sound, can we have something tonal, like a note on the piano? Because if it's going to pitch shift, right?
Yeah.
It will be easier to tell.
Well, this is somewhat pitched, but I guess a piano. I like that I'm scrolling through. That's MIDI. God damn it. There we go. All right. Good enough for government work. Here we go. Oh, I disabled the master, but that's probably unnecessary. We trust loser. Famous last words. Well, that's the sound it made.
I didn't hear that. I don't know if the stream heard it, but
it went it kind of clicked and nothing interesting happened. Yeah, it just went so without, I think you'll hear that. And everybody hears that piano.
Yeah.
And with just sounds like tick, tick, tick. It sounds like 3 clicks. We can render it so that we can see.
Maybe
yeah, it just sounds like,
because of the technique that so I know for a fact that the plugin by default is going to try to make things faster, so it's going to take the pitch higher, and the whole technique that we are talking about is going to make a read head move faster through the audio. So if you just have an attack, a very transient sound, we may not hear anything because it's gonna go so fast.
oh, okay.
But
like, should I get something longer?
Yeah, maybe if you have a pad, we'll hear something more interesting. But also, I think that the slider was wrong.
The slider was at 0, but so basically the resulting output was essentially like this.
Yeah, but the slider being at 0 is not going to do any do us any favors. Can we have the slider at 1.5?
Sure. Okay, I'm putting a pad and okay, yeah, that's doing something. It's very clicky, but I guess that's a basic.
In the end of the tutorial ends by, now one could simply crossfade the jumps between each buffer to get rid of the stuttering. And then he would have a pretty decent pitch shifting effect. So this one is not doing the
Smoothing.
2 playheads and crossfading. It's just doing one of the playheads. We would have to work extra to make this work. But before we even do that, so it is pitch shifting. It's just not doing a good job. It's not sounding too nice, but it is pitch shifting. So
sample rate divided by 8. Very interesting. And then is sample.
Yeah, so what I propose is that we make sense of what's on the page right now.
Okay.
Let's read through the tutorial and try to understand what it's doing. Then maybe we can try to do the crossfading, and then we let you bring it into the bigger effect.
Okay.
Okay, so it starts simple. In fact, I would say that it starts perhaps too simple. It's simplifying things that we tend to make more explicit in our code. So it has this buffer of samples that we call like a circular buffer, and we tend to have an init block where we say buffer equals some address and we allocate some memory and all of that stuff. But here in this code, loser is just saying bpos is a variable that if has not been defined before, so it's just 0. So the base address of our circular buffer is 0. And it's taking that and it's storing sample 0 in that position. And things are going to get weird in a moment. Next line, it's taking the sample rate and dividing by 8. What the hell is that? Well,
yeah.
If you read a little bit below, it's going to say that sample rate divided by 0 is about 125 milliseconds. So that's the size of your grain.
Okay.
Or the length of your
grain. That
grain.
makes sense.
125 milliseconds. So, but why? So that's okay. That's the size of your grain. But why are you saying bpos at that position? Well, that's because this effect is stereo. So the way he's organizing the memory layout here. So remember that the notion of memory in JSFX is there is a big chunk of memory. Do whatever you want with that.
Yeah.
And we tend to use memory allocation functions and all of that to make sense of this and try to put some order into the chaos. But you can just use memory like that. So what he's doing here is he defined a layout of the memory that is the first channel is going to be sample rate divided by 8. So it's going to be 125 milliseconds for the left channel. And then right after that, there will be another buffer for the second channel. It's a stereo effect. So if you take position 0, that's where you store your left sample. Then you skip ahead in memory. So you're giving yourself space to store other samples for the left channel in the future. It's going to skip ahead, just sort of reserving that space in memory for the left channel. And then you start writing the right channel there. So in essence, you have a big chunk of memory. How do you use it? In this case, take a chunk of that and call it left channel, and take the next chunk, call it the right channel. And that's the second line. This code is so nice because it's so short, right? It's literally 5 lines of code. And when I first encountered this, I was like, oh, that's so cool that you can do something as cool as pitch shifting with 5 lines of code. But at the same time, it's kind of difficult to understand. At least
a bit crazy.
It is to me.
It's
some parts of it. Yeah, it is very clever though. This whole thing of sample rate divided by 0, and then you do it's very clever code. I really like it. And before we look into the 3rd and 4th lines, I want to bring our attention to something that happens on the 5th, the last line. So you see in parentheses, it says bpos plus equals 1.
Yeah.
So that's something that is sometimes called pointer arithmetic in languages like C and C++. Typically, the way that we reason about arrays or chunks of memory or buffers, however you want to call them, is you have your base address. I think that's even why it's called bpos. It's like base position, something like that. So you take your base address and then you index into the position that you want. So if you have an array of 5 elements, you have your base address and you say my base address and then in brackets position 0, position 3.
Yeah.
And that's how you navigate in that array, right? But that's not what loser is doing here. Perhaps because it's shorter, perhaps because it is cooler, what he's using is pointer arithmetic. And the way that works is you take your base address and you move it around. So you can see that in lines 1 and 2, the index is always 0 and sample rate divided by 8. He's not changing the index. He's changing the base address itself. So the way that he's advancing a pointer is not by keeping a sort of index variable that he would increment on every sample. No, he is taking bpos itself plus equals 1, so he's advancing the base pointer.
Okay, yeah, interesting.
Cool stuff, huh? So, of course, as you are advancing the pointer, at some point you will have reached the end, and you will know that you will have reached the end because you see this greater than or equals to sample rate divided by 8.
Okay.
Sample rate divided by 8 is the length of the buffer,
Yeah.
right? So he's doing 2 things on this line. Well, actually 3. He's doing 3 things in this line. The first thing he's doing is he's saying bpos plus equals 1. That's going to advance the pointer, the base address. The second thing is he's comparing. So when you just say bpos plus equals 1, what is the result of this expression? It is the updated base address. Yeah. It's whatever bpos is right now. So he can use that value in the comparison. So he's comparing greater than or equal to the length of the buffer. So if I am past the end, then this will be true. And then question mark.
So if that happens, just reset it.
Yeah, so just say bpos equals 0. So
back to square
puts the pointer back in the beginning. So with these 3 lines, or actually with just this last line, he is taking care of managing the circular buffer.
Yeah.
So with a single line, he's managing the circular buffer. In my implementation of the circular buffer, I have a page full of code. It took me months to get it to a page full. It was much more code before because I was making things more complicated. So the brilliance, the simplicity in this line is just amazing. He's doing all the management in a single line. Very clever code.
Nice.
So that's the line that is updating the pointer into the circular buffers. And in the first 2 lines, he's just using the circular buffer and putting some samples there, collecting samples to replay later. Nothing fancy. Now, the meat is lines 3 and 4, where he is replaying from the circular buffer. So let's try to make sense of what's happening there. So we see an expression in parentheses. This expression is bpos times slider 1. That's the expression that is going to compute a base address. Yeah. And then we see square brackets. So we know that this is accessing into the circular buffer, as one would expect, right? Because the point is that this is going to replay. So it's going to collect some sample from the circular buffer. So what's on the left side? That's the base address. So you take your base position and you multiply by slider 1. Slider 1 is the pitch. So at 1, this is just going to be the base position. It's not going to do anything. But if you say like 1.5, which is the default when the plugin loads, you are going to skip ahead. So you're going to be faster. You're going to be playing at 1.5, the original rate.
Fifth.
Yes. No?
Yeah.
I don't know.
Yeah, it's a fifth. Because it's a 3/2 ratio.
Yeah, there you go. So, and then there is the thing in brackets. The thing on the left is the base address. The thing on the right is the index. And the index is something relatively crazy.
Yeah.
So let's try to make sense of that.
I don't get the floor bit of it.
You do?
I don't. Like, I know what floor is, but I don't know what it's doing here.
Yeah, so let's work this from the inside out. Inside the floor, we see bpos times slider 1. That's the same thing that happened on the
Right.
left. So we know what that's about. It's just playing things faster, skipping ahead, getting to later samples if you are playing at higher pitches, or getting samples from the past if you're playing more slowly. If you're below 1 on slider 1. So it's just that. But then it's dividing by sample rate divided by age. Sample rate divided by age is the length of the buffer. So it's dividing by the length of the buffer. So we know that bpos will always be between, so let's think about the left channel, just to make things simpler, because we are looking at the line that is working on the left channel. So we know that the bpos is only going to be between 0 and the length of the buffer, because when it gets to that size, it wraps back. So it's a number that is guaranteed to be between 0 and s rate divided by age. So when you take bpos times slider divided by s rate divided by age, you are guaranteed to have a number that is in that range.
We can even get the number. I mean, I know what my sample rate is, and actually, why is it not in the sample? Yeah, it's 48,000. So it is very easy math, because it's 6,000. 6,000 samples.
There
right?
you go.
Yeah. Okay.
6,000 samples is the size of our
Buffer.
But there is a wrinkle. It's multiplying by slider 1. So this number is not going to be simply between 0 and 1.
Right.
And then it's taking the floor. So this number, again, is not going to be between 0 and 1. So the floor is not guaranteed to be 0. The floor can be greater than 0.
But hold on. Wait, one question there. So the maximum, because slider 1 goes up to 5, right? So 5 divided by 6,000 is going to floor to 0. And then bpos is never going to be bigger than 6,000. Oh, but okay, I see. Yeah, the bpos can be like 3,000, and then times 5, that's 15,000 divided by 6,000 is not between 0 and 1. Gotcha. Sorry, I just had to say that out loud.
Yeah, so this number is not going to be between 0 and 1. So the floor is not going to be between, or the floor is not going to be 0. The floor is going to be some interesting number. Then you are multiplying by the length of the buffer again. So you got this number that was relatively small. You truncated that number using floor. That's what floor is going to do. You're going to have a number like 2.75. Floor of that is going to be 2. And then you're multiplying again by the length of the buffer, and then you're taking the negated value. You're saying minus in front, right?
So minus 12,000.
So what you're doing is you're going into the past because of this minus.
Okay, gotcha.
So the whole thing that we are doing here, when you divide by a number, take the floor and multiply by the same number, that is a way of reducing the resolution of a number. You know what that is?
Yeah. That's
the essence of a bit crusher.
Yeah, exactly.
That's the formula that you would use for a bit crusher.
Yeah, that's why I thought bit crusher would be really easy. We just take the SPL and like take a few decimals off, and you got a bit crusher.
Yeah. It's more interesting if you want to do something like oversampling or band limiting, so you don't alias the output. But yeah, a basic one, in fact, was my first video about JSFX. So that one is relatively straightforward. So it's kind of neat that we circled back to a bit crusher when implementing the pitch shifter. Okay, so that's more or less what we are doing. We're just taking some samples into the past. Now, SPL1 is sort of the same, except that there is a plus s rate divided by h. That is just going to take you into the next buffer, right? Because we're just adding a length of a buffer to the beginning. So it's exactly the same formula, just shifted to the right. So that's how this works. But I propose that my favorite way of reading code is to actively read the code. So when I see something that I don't understand or I don't like, I rewrite it.
Yeah, namely, I'm like the S rate divided by 8, like, don't necessarily need to use that amount, right? In fact, you give that as a parameter to the user, they can kind of change the flavor of, because it affects the tone of the pitch shifting. If like it's a shorter buffer.
It will affect.
Yeah.
Yeah, it will affect the quality and the smearing. Yeah, especially when you are going for special effects like we are.
Yeah.
Because you could be doing pitch shifting to try to correct a vocal performance. In that case, you want to be transparent.
Right.
But if you want to be crazy about it,
yeah,
and that's what we are going for, right?
Yeah.
We better do it. Right, so the first thing that stands out to me, yes, is this sample rate divided by 8. Not only because of what you mentioned, you can give it as a slider to the user, but also you're dividing by 8 a lot of times, and dividing is never fast. So
you can just make one
better, and we'll make it we'll make it slightly faster, maybe even.
Yeah, so you just say something like buffer underline size, and you say that equals to straight divided by 8, right? And then you just replace it all over the place with the stuff. Let me see if I remember the cool replace trick. Oh, Command and R replaces. So I'm looking for S rate divided by 8. Nope, you're gonna lose it. Oh no, okay. Once you hit Command and F, your mouse won't work. S rate divided by 8, and then you can go F3 to go to the next one. Oh no, you press Enter first, then you go F3. And you replace it by Shift and F3? No, that's previous. Oh, you just... Wait, what was replacing? It was Command and R. But that didn't do it. Oh, replace all word match buffer size. And then we can just change this first one to S rate divided by 8. Cool. I just wanted to throw this trick into the mix.
Yeah, so how about, this is low-hanging fruit. How about we have a slider block where we give this buffer size a slider, and we can hear what that sounds like.
But you mean give it a real slider or yeah, like just have a slider?
No, we'll need both. We need an actual slider.
And we need a slider block.
Yeah, or maybe not, right? We can have a buffer size whose range is something that makes sense. So we don't need to take S rate divided by 8.
Yeah. I'm thinking, yeah, then we can just get rid of that. I'm thinking like it should be something like maybe like 30 milliseconds, because below that like pitch perception is wonky anyway. So 30 milliseconds to 1,000 milliseconds to 1 second. So it'd be from, well, 48,000 would be the max. And 3 milliseconds would be... 480 times 3 is 1440. But how does that sound to you?
Ah, amazing. I would not even try. I pulled out a calculator to compute 1.7 plus 1.7 on Friday.
Oh, come on. That's funny. I already forgot the values we said. I guess I'm also like assuming people's sample rate, but whatever. I'm not sample rate woke.
Yeah, we can always... You can always give this in terms of milliseconds and then compute the number of samples.
Oh, that's probably way smarter.
And that's why I proposed that we had a slider block, because
so
to
we
go
do
from
that.
the slider value into the buffer size, we would compute that in the slider block.
Yeah, that's like so much more logical. I guess not more than half millisecond, really, right? Like if you're hearing the difference between 3 and 3.3, like you're lying.
No, you're not.
Yeah, you know. So buffer size, I'll do ms. And then, so we make a slider block. I'll get rid of that code, or I guess if I just replace that with slider2, slifer2, right?
Yeah, and you want to change from the init at init. You want to change that into at sample, so it reruns. Or sorry, at slider.
Yeah.
So it reruns when you change the slider. But you don't want it to be just slider 2, because slider 2 is in
I
milliseconds.
see. Yeah,
you want to have that in terms of samples.
Yeah.
So you need to go from milliseconds to samples.
Which you have a thing for that, but
yeah, it's in the library, but it's so simple to do. It's just times 1,000 divided by sample rate.
Oh, and I gotta parenthesize.
No, it's the other way around, isn't it? It's divided by 1,000, because that's going to give you something in seconds, and then multiply by the sample rate.
Divided by 1,000. So if it's like 3 milliseconds, 3 milliseconds divided by 1,000 is 3,000, and you times that by the sample rate, which is 48,000. Yeah, that makes sense. Times.
Yeah, so multiply by s rate. And that's your buffer size.
Perfect. I guess I should say call this buffer size. Yeah, what am I doing? That's dumb. Let's just put this here. All right, and put one of these. God damn it. All right, here we go.
And let's hear this guy.
So I guess like it's still gonna click, but we did give it some bells and whistles in the meantimes. So pitch, let's keep the pitch at a fifth. Oh. There we go. Click aside, it sounds good. And like the longer your window size is with pitch shift, that means you get more tone. Like you get more, like the smaller it is, you have like fewer times to generate long waveforms, right?
Yeah, I guess the trade-off is,
if it's smaller, it's more like a pure pitch shift. If it's longer, it can, like if it's 1,000 milliseconds and what you're playing is rhythmic, you're also generating rhythmic like variation. Like you're taking, like if I'm playing like staccato notes, like do 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 do, then the pitch shift will not only pitch shift, but it would add like an extra rhythm that's like faster as well.
Yeah, that's what I was going to say. I think that in terms of the quality of the shifting itself, you want to reduce the crossfading between the grains. So you want the grains to be long. But if you want the pitch shifting to catch your notes faster, like when you are playing, you want the pitch shifting to respond, then you want your grains to be short because you are going to get to the samples that are coming in faster. So that's the trade-off: a response to transients versus the quality of the shifting itself.
Have you seen, this is a good tangent, have you seen Hourglass?
No.
Xenakios made Hourglass. It's one of the reasons I'm not upgrading from Mojave, because it's no longer supported post Mojave. And it's like a standalone app, but Xenakios is like somebody who's done a lot of ReaFIR scripting as well, but they're out of that community now. But yeah, like it's one of those things, you know, like when you see like, oh, this is like Metallica's Nothing Else Matters, but like it takes 19 hours because they slowed it down so much. They do it with Hourglass. So it does like...
Hourglass, I know that as Po stretch, and then the version that Xenakios did was like Po X stretch or something.
Okay, yeah. Hourglass is it this similar, but Hourglass has more like like a lot of extra stuff as well. Randomization. It has envelopes, so you can change all the rates. It's like super. It's so good for sound. Remember that cat thing that I showed you? That was made with Hourglass. So you can take like one cat meow and generate a swarm of cats that are attacking you.
Yeah, so it sounds like yeah, I'm trying to find what's the difference between Hourglass and PoX Stretch, because made by the same person,
Yeah.
does the same thing, and I don't know.
Well, the difference, I guess, is that with pole stretch, you are doing extreme stretching. With Hourglass, you do extra things that may not necessarily stretch. Like you can have, for example, also the playhead make random jumps, so that not only you are stretching the file, like making the file longer, but the generating file is like never a repeat. Like it's not just like taking a thing and stretching it. It's stretching it by jumbling up its samples like 1,000 different ways and making it like a really long file.
Amazing. Yeah,
Super
I'm
cool.
really into that kind of experimental and let's say it weird.
Yeah.
I like it a lot. Yeah, I'll look into Hourglass. So I guess that's another reason to have a secondary computer around, like a Windows machine, because you can just have an older version of Windows, who cares? And then you can have all these somewhat aging pieces of software just around. Interesting. Yeah, but that at least post-stretch, I don't know about Hourglass because I've never heard of it before, and from the page I cannot make sense. But post-stretch is not using this idea of multiple grains and whatnot. As far as I understand, it's doing something else. It's using FFTs.
Because it's also offline. Like it doesn't need to be an online. Like it processes the audio versus being a real-time effect. So like the game is totally different.
Yeah.
Right.
Cool. So we have that, but there are still more things that I think we should change about this code.
I mean, like this thing down here, like it's super clever and I'd be down to not change it, but also like the logic of what we've done with all the other effects is different. So I don't know. What do you think?
Yeah, the reason why I propose that maybe we change this is that we want to have 2 grains and crossfade between them. So we'll not need 2 buffers for left and right. We'll need 4 buffers for left, right, previous grain, next grain.
Yeah.
So then we were taking B pause at 0, B pause at buffer size, B pause at buffer size times 2, B pause at buffer size times 3, and that will get out of hand.
Yeah.
So I propose that instead of having pointer arithmetic, we have 4 buffers.
Yeah.
That we read and write from.
Yeah.
And to do that, you need an init block.
Yeah.
And we are going to be pessimistic in memory allocation, as one does, because you don't want to allocate memory after the fact. You want to allocate memory up front. So we will allocate 4 buffers. We may call them like previous grain left, next grain, or maybe it should not maybe be previous and next because they're going to change roles. So let's just have grain 1, grain 2 left, grain 1, grain 2 right, and they need to be pessimistic. So they need to be as big as the biggest buffer we may ever need, which is buffer size of 1 second.
Oops. I don't know why. My angle is weird from my keyboard, so I'm writing everything wrong. Boom. And then zoop, boop, zoop, boop. I fucked it up. Well, I meant to do another thing, but whatever. This is fine. 1L1R, 2L2R. Cool.
Yeah. So what is the biggest buffer we may ever need? It's 1 second. So it is
1,000
1,000
or
divided by
48,000.
1,000 times the sample rate. So it's 48,000, which means that grain 1 left will be at 0, or 48,000 times 0, if you will.
Right.
Then the second one is 48,000.
So should I just hard code 48,000 or should I still times it by S rate? What do you think?
Well, I would. Oh yeah, we are using S rate on the other one. So I would just say S rate times 0, S rate times 1,
Cool.
S rate times 2. Maybe I would even say like 1,000 divided by
S rate.
1,000 times S rate. Just so it's very clear. But you know what? I probably would have used my library instead, where I have a function that reads like milliseconds to samples or something like that. And I would be using the memory allocator from the library as well. So, doesn't matter.
Cool. I guess, I don't know. Well, now that we're writing a new thing, should we just use your library? Or I guess we're implementing it into the older
thing. We are prototyping. We are prototyping. Oh, you know what? Now it comes to mind that S-rate may not be available on the init block. I don't know if it is.
Oh, so this is a good...
we need to double check this.
I think it isn't.
Yeah, well, we can easily check this. You can just make this code syntactically correct again. So
I'll just comment out these 2 bits.
Yeah, you can comment this out.
Whoa. Wait, how did you comment? Oh, it was this shit. Joops, zoops, or joops? Yes. It's very interesting. I'm very good at dictation of languages, but syntax-wise in coding, I'm dyslexic. I always get things the other way around. Zoink. And
so let's check if the grain 1R is not 0. It should not be 0.
Grain 1R. I wish there was a way to get rid of GFX stuff until... Yeah, it's not 0.
Well, it is weird, isn't it?
It is a weird value.
Yeah, because the mathematics is wrong there. Look at the formula we have below and the formula we have above. They are not the same formula. What we want is just to replace slider 2 by 1,000. The parentheses are in the wrong place.
Slider 2 by 1,000? Oh, wait, here.
Yeah, so there is our formula. That formula is correct. We checked it. So what we want above is to have, instead of slider 2 in that formula, 1,000, which is the biggest value slider 2 can hold.
Oh, so it's like this, you mean? Am I getting you right?
Yes, you understand me right.
Okay.
And to be pedantic, you don't need the parentheses there, but it seems like the parentheses help you read it, so you can keep them there. But the parentheses are not doing anything.
Yeah, okay. Cool. And then, I gotta do the same thing, obviously, for the right one. Zoink, boing, boing, joink, doink, doink. Okay, yeah,
and
that makes sense.
That's more like it.
All right, so I'll just keep going. Zoops, dos. And then zoops, tres, zoink. Cool. So S-rate is available in the init block.
Awesome. So let's try to reconstruct the same effect without really using the second grains. Let's just use the first grains and try to reconstruct the logic that we have on the sample block, see if we don't break anything. So anywhere where we see bpos at 0, well, we only see it in one place. But bpos now should not be bpos.
Should be grain L.
The position it should be grain L.
Here's something. Let me know if you agree with this. This IDE window should have like a small border. What do you think about that? It really bothers me.
I don't care one way or the other. I don't tend to use this.
Oh, okay. Cool. And then this.
But we do need it. So
we do
before
need
we
the
even
base
move further,
position, right?
yeah, so this 0 there was working because of the pointer arithmetic, but I think we are getting rid of that, right? We are going to keep the base addresses fixed. So we do want to have some sort of index variable that will loop around, and we'll put it there instead of the 0.
Yeah. So we can call it buffer index. Why not? What do you think of that?
Sure.
And it just starts at 0, right?
Fair. Okay.
Or do you like starting it at -1, the thing? If that makes
Doesn't really matter all that much. It's just a single sample when the plugin loads.
Right.
And the way that this is written, we are updating the buffer index, which used to be called bpos, but we are calling it buffer index now. So we are updating it on the last line of the sample block. So saying that buffer index starts at -1 would be incorrect because it really starts at 0. You would start it at -1 if you wanted to do the thing that I usually do, which is to update the bpos as the first thing. Okay, so far so good. Now for the second line, bpos at buffer size, we want to use grain1 R at buffer index.
Actually, this will probably be easier to do like this. See, I don't like this space because it's hard to put your shift here. It puts the resize thing there, and then this becomes SPL1, and this becomes R. Okay.
Good. And then let's go to the last line and update the buffer index.
So we want to go buffer index right here plus equals 1. I don't know why I'm doing that. All right. This is
if it's greater than or equal to the buffer size, then you need to say buffer index equals 0.
So this is just for us to not, we're still not using the read stuff.
Well, we are using this buffer index, I would say, is the write head. That's where we are collecting samples. And we don't have a variable for the read head because we don't really need one. We can recompute this read head as we go.
Okay.
Because the read head is where things get interesting. The write head is just a plain circular buffer moving around, easy stuff. The read head is where it gets interesting. The read head is the one that gets faster or slower.
Yeah.
So we need to recompute its position every sample anyway. So there isn't really a point in keeping it around that like that.
Like in case, because we gave a slider, we have to recalculate it. Like if we had a fix,
that has always been a slider.
If we had a fixed buffer, would we have to recalculate anyway?
Yes, because of the pitch that has always been a slider.
Okay, I see. Yeah.
Yeah, the pitch can change. Yeah, so now it's the kind of complicated part. So let's try to rewrite these two lines in the middle, the lines that start with SPL0 equals and SPL1 equals. We'll try to rewrite this in a way that doesn't break anything, using grain1L, grain1R.
Cool.
Well, SPL0 equals grain1L, that's the easy part.
This needs to be buffer index times slider 1.
Well, no, I propose that we start with, maybe write this line above, so we have the line there as a reference. But what we want is SPL0 equals grain1L at, And this is where it gets interesting, because we need to compute the right index. That's our read head that we need to compute to make this whole thing work. So we are going to take our buffer index. That's our our write head. This is our current position in the circular buffer. And we want to move it around. We want to move it around based on slider 1. So I guess we can start with buffer index times slider 1.
Or maybe we're not.
Next, so this is already moving that thing faster. It's going to go into the future faster. So if your buffer index, your write head, is at like position 2, and your pitch is, let's say your pitch is just an octave. It's 2.
Okay.
Making things easier for ourselves. So if your buffer index is 2 and your slider 1 is 2, you're already in position 4. So you're going faster. Great. But we cannot go faster into the future. We haven't collected those samples yet.
Yeah.
So we need to go faster, but we need to wrap back into the past. Or maybe we can go into the future. Think about this. This is a circular buffer, right? So if you go into the future, you're just looking further into the past.
I see. Fun. Here's a question before we move forward with this. So already because of this, so for simplicity, let's say this is 2. Does this mean that we're kind of skipping every other stored sample that we put in grain 1L? Yeah. Interesting.
Because you have to play 48,000 samples in a second.
Right.
And you are collecting 48,000 samples in the circular buffer. That's the size of the circular buffer when you're using the maximum grain size. But you are playing at double rate, double speed.
So
So you want to play 48,000 samples at double speed. You're going to play 24,000 samples.
Yeah.
Right. So you're throwing half of them out. And if you want to be very precise and correct about this, you probably don't want to just throw half of the samples out.
Yeah.
You probably want to use some oversampling, and you want to do some filter to cut the frequencies that would have an image above the half of your sample rate. In this case, your sample rate is 24,000 samples.
Or your Nyquist.
No, when you're speeding things up, I'm saying all this in reverse this whole time. When you're playing things in double speed, you're going to play 96,000 samples in a second.
So
right?
you gotta,
just skipping ahead. So you have to do some alias filtering, anti-alias filtering, to get rid of some distortion. And yeah, it gets, of course, more complicated than 5 lines of code. But it's a good start. This is called decimation. You're just throwing out samples you won't use. And decimation is particularly bad when you have something like a pitch ratio of 1.5, because then you are not skipping from sample 2 to 4. You're skipping from sample 2 to like 3.5.
Yeah.
And then you need to compute the sample in between.
Jeez.
So, yeah, of course it gets complicated.
Yeah, crazy, eh?
Yeah. So
okay, so right now we basically wrote one bit of this, but we still need to do this bit, right? Like from the square bracket up.
Yes. And I'm having a hard time really understanding what we should be doing here. So I have an idea. We can do something that is relatively simple. You take this expression, buffer index times slider 1. And one thing that I know for sure is that this calculation is going to go above, it's going to grow bigger than the buffer size. Because if the buffer index is more than halfway through, then the slider may be like at 2, and then you're going to go above, right? So that's one thing that we know for sure. So how about we do something that I know is super simple to do, and that will guarantee that we will be between the bounds.
Okay.
We'll be in bounds. So the thing is, you take the buffer index times slider 1, put parentheses around the whole thing.
Yeah.
And then after the parentheses, you use the percent sign. Do you know this operator?
Yeah, that's the modulo.
Exactly. Yeah. And you take that modulo, watch. Do you know what I'm going for here?
You wanted the modulo to be as big as the buffer size, right?
Exactly. Yeah. So you say buffer size there. So now we are guaranteed to have a number between 0 and buffer size.
Cool. Yeah, modulo, if somebody watching doesn't know, though I guess everybody does, is it takes the modulo of 10 to 4 is 2 because it's goes 1, 2, 3, 4, 1, 2, 3, 4, that's 8, and then the remainder is 2. So it's modulo gives you the remainder after the division is done, but only to whole integers, so it doesn't go into decimals. Because 10 divided by 4 is like 2.5, but modulo 10 by 4 is just 2 remaining.
Yeah, you can think of a modulo as the remainder of the division. It's not that. Strictly speaking, it's not that. It gets more complicated. But in JSFX, it turns out, like in C and C++, it turns out that this code is going to work for us. If you wrote the same code in JavaScript, for instance, it would not work because modulo is going to do something closer to the mathematical definition of modulo. But let's just think of this as the remainder of division.
Cool.
So you can think of modulo as remainder instead, if you prefer. Right, so the remainder of division between whatever and buffer size is going to be between 0 and buffer size.
Yeah.
So that is already something that is going to be in bounds.
Cool.
So I propose that we put a semicolon there. We do the same thing for SPL1, so we get a stereo effect. We comment out the next 2 lines that we have for reference, and we hear what that sounds like, because we may be getting closer to something that works.
And all I gotta do is this, and let's see. Come on, dyslexia. Come on up. I got it wrong. And then last line we keep.
The last line is taking care of the updating the buffer index, yes. So let's hear what this effect sounds like. Maybe let's mute the master for a moment. But I don't think that this is going to go too loud because we are never multiplying by a scalar.
We're not changing. The input and output are the same. All right. So wait, I'm going to go back to 1.5 as our control group.
Play with pitch.
That sounds great. Like clicks aside, that's actually a very good sounding pitch. It has especially the slider. It has a very nice, yeah, it's very nice. I love it. I'm going to be using this.
So I think that we got the logic right. This whole modulo thing seems to be working well for us.
Yeah.
It sounds like a pitch shifter to me. So I am just proposing that we ignore the rest of that computation that we didn't fully understand, the negative floor stuff.
Yeah.
I think that this amounted to the same logic as what we have on the screen, which may be a bit more verbose. We have more variables going on, but I think that our thing makes more sense.
Sounds good to me, yeah.
So I have a proposal. I have a proposal that, you know, when you were playing with the slider, there was something that the pitch slider, not the grain slider. The grain slider was all over the place. It was just mostly clicks.
Yeah.
But the pitch slider was super cool because when you played with it, it sounded like a tape.
Yeah.
Kind of sounded like you were slowing down a tape. And it was also kind of clicky.
Yeah.
And there are 2 reasons for that. The first is we are not we're not crossfading grain 1 and grain 2 as we should. But the second reason is what I just mentioned. Sometimes your pitch is 1.5, so you need to go to sample 3.5, right? You need to compute the sample in the middle. So my proposal is that we implement a very simple oversampling mechanism.
Okay.
How about that?
Sure.
That is going to give us the smooth values as we move that slider around, which is already more than read-LA can do for you. So yay for us. But it's going to be a simple oversampling, okay? It's going to be simple. Sure. It's going to be simple.
Yeah, cool.
We are going to use linear interpolation. Have you heard of this?
Yeah. Because it goes beyond just oversampling, right? It's just like, interpolating between two values.
Well, that's the essence of oversampling is. You're just computing samples in the middle. So, okay. We are going to do oversampling just because it's so simple. The crossfading of the grains, that
is harder.
Is not too hard, though. You know your buffer size, your buffer index is something that is going to give you the position in the grain.
Yeah.
So you multiply by the buffer index by slider 1, and that give you the rate at which you are consuming the grain. So you can just compute a window that is not rectangular, a window that is smooth in the beginning and the end. So you can take this window and multiply the value of this window by the sample, and you will be smoothing in and out. So you just have to, the harder part is probably to overlap the two grains.
You know, the crossfading scares me because also when we were doing the EQ thing, the ramp bits, I never got, and I know I made a daemon out of it, but like the ramp bit, it never got in my head, and I even watched your video and kind of just copied it, and it never worked. So crossfading should be interesting.
What do you mean by ramp?
Remember with the EQ, to make it like smooth, so that it doesn't click if you move the values around. I had to implement the ramp. I never got it to work.
Ah, interesting. So okay, you know what? Now we need to fix this situation for you. Let's go to the slider block below where you have, or above.
Okay.
Doesn't matter. It's up to you. Where you have buffer size, have a variable that you call maybe speed.
Okay.
And speed is equal to
slider 1.
Or maybe plus equals 2.
Okay, cool.
Speed plus equals 2.
Okay.
Slider 1 is our pitch ratio minus speed.
Okay. Wait, let me
So what do we have there?
Logic this. So speed is increased every time we go around the slider block. Say the value is 2. So it's 0, it goes 2.
Let me ask you to rewrite this.
Okay.
Instead of using plus equals, let's do it the full hand.
Okay.
The complete thing. It's speed equals speed plus slider 1 minus speed.
So let me, speed is a function?
No, plus.
Oh, plus. I see. Okay, so let me think about this in my head. So at the beginning it's 0. So this is 0.
No, so forget about it. Just look at the formula that you have there. You have you have speed minus speed, don't you?
So you just have slider 1.
You just have slider 1. So speed is exactly equal to slider 1.
Oh, okay.
Right. Okay, so that's what we begin with. Let's begin with that.
Okay.
So what is slider 1 minus speed? That's the difference between slider 1 and speed. That's slider 1 is where you want to be. That's what you want the ratio to be.
Okay.
Minus speed is where you are.
Yeah.
So you're traveling that distance. Plus equals means travel the distance between where I am and where I want to be.
Cool.
Okay, so if you go there immediately, it's going to click.
Yeah.
because you're moving too fast. How do you smooth things out? You move more slowly.
Yeah.
So you take this slider 1 minus speed and you move more slowly. So you divide by a value or you do something. You make this value be smaller. The way that some plugins I found do it is they divide by a value. The way that I prefer to do it is you just take the minimum, you just limit the value. You truncate the value. You say, the same way we had a code in the tutorial page for a limiter that was just truncating a value, we truncate the value. So we take this slider 1 minus speed and we say we want the minimum between that and like, say 0.1.
Okay. I forgot the syntax of min and max.
It's just exactly what you wrote, and then slider minus speed is one of the parameters, comma.
Okay.
And then let's say 0.1 is the other parameter.
Cool.
And then you also take the maximum between this thing, the whole thing. So you say, right, before min, say
max of min, I see.
Yeah, so the result of the previous minimum, you take the maximum between that and say minus 0.1.
Oh, sorry, that goes minus 0.1. Syntactically, there's no way I didn't fuck this up. 1, 2.
So this thing that we have there, it's actually correct. Yeah, so the thing that you have there is you want to travel the distance between where you are, which is speed, and where you want to be, which is slider 1. But you're limiting your speed. Well, isn't this funny? You're limiting the speed at which you're traveling by saying my car doesn't go faster than 0.1. So if I want to get there, I will get there in at most 0.1 steps, or sorry, steps of 0.1 length. And probably 0.1 is too big of a value for this. You probably want to go smaller than that. And you don't want to necessarily, I told you to put this in the slider block, but that's incorrect because the slider block is only going to change when you move the slider.
Yeah, put this in the sample.
But you want to keep doing this every sample.
Yeah.
And you want to keep updating every sample. And of course, if you reached your destination, slider 1 is equal to speed, so slider 1 minus speed is going to be 0. So it's going to be speed plus equals 0. You're not going to move. So that's how you smooth things out.
Okay.
Or at least one way of.
So I guess what trips me is like this max min thing. If this is a constant, maybe this is for your library. You make a function called ramp.
Yeah, I call this, I think,
or something,
smooth.
Smooth, okay.
Something like that.
Because it seems like if something you gotta use this every time, like, wouldn't it be great if you didn't?
Yeah, I have that in the library, and the technique we are using is something called a slew limiter. Slew is rate of change, and we are limiting the rate of change. You're not allowing the change be so fast.
Cool.
You know what? Here's something we can try. Change this 0.1, which is too big of a number, to be like 0.000, a bunch of zeros, 1. So it's a very small value. And of course, the same for the other one. And then you move the slider around and look at the debug window, and you see the speed variable changing more slowly and following.
Oh, cool.
Your slider. Yeah, so try that.
I guess I gotta save it for speed to show up. Why is there a speed going on? Oh, because it is going through samples. It's live. Okay. So the speed is, if I slow down, this number gets bigger.
No, speed. You can stop the audio. Speed is just following your pitch ratio slider. So if you just wait long enough, speed is going to be 5. And when you move the slider, it should be following. So I guess 0.000, we have too many zeros there. It's moving there too slowly.
Oh, I see. Can I hear that for a sec?
Yeah. But we are not using the speed variable.
Oh, it's not kind of, so it's still doing that thing. I see. Okay,
Yeah,
the
we're
value
still
is
using slider
arriving
1.
late. I see. So the value starts at 0, goes to the value of slider 1. So just to make this like hella small, and I guess I'll take 5 zeros off. What do you say?
Yeah.
1, 2, 3, 4, 5. I could also do it another way, but zoinks. So between 0.1 and 2,
now you can see that it's 0.2. And I guess maybe this is too fast, but you sort of see some values in the middle.
Yeah. So if I go whoop. There we go. Now that seemed like too much. 1 extra 0, but whatever.
In fact, when I implemented the function, the longest time I spent not implementing this, but just finding a value that worked well, that would not produce clicks, but at the same time would not be too slow, because you don't want to hear that fade, probably, depending on what you're doing.
I'm just gonna do this thing so that I don't have to all the time do the thing.
For what it's worth, for volume at least, I found that minus 60 dB worked well.
Minus 60 dB?
Yeah.
As in the speed is?
Yeah, just take 10 times minus 60 divided by the 20, so that is... That's the value that worked well for me.
Cool. All right, so I guess we'll dial in this value.
Yeah, the value that worked well for me was 0.001. That's what it is. I put it on Google. So 10 to the power of minus 60 divided by 20 is 0.001.
Cool.
And that's a value that worked well.
It would probably work here as well. I guess the speed isn't still in the code, so I guess let's do that.
Yeah, and you want to change everywhere in the sample block where you read slider 1, specifically on the lines that start with SPL0 and SPL1. You want to change that into slider 1 into speed now. So we are now smoothing out the speed.
Speed. But not here. Oh, because we don't have speed yet. Yeah, I see.
Yeah, you're calculating speed there.
Cool.
And for good measure, I would probably in init block, I would have speed equals 1.5, just so when the plugin loads, speed is not 0.
Cool. We can also give speed to people, and then if they slow it down, it would have like a portmanteau kind of effect, almost like a glide.
Yeah.
Cool, fun.
Yeah. You probably want to don't want to have speed equals 0. You want to have speed equals slider 2, or I don't know if the slider variable is available in the init block, but 1.5 will be. So there you have it. So that's how you smooth a variable. But now let's do the thing I promised, where we do the oversampling, and then we can
cover today as well, after oversampling.
Yeah, so linear interpolation is just, we want sample, let's say sample 3.5. We are going to take sample 3, sample 4, and average. Or if we want sample 3.75, we are going to take sample 3, sample 4, and we are going to get a weighted average, where sample 4 has a weight of 0.75, sample 3 has a weight of 0.25, and then we take the average, and that's our sample in between. So we are just pretending that there is a line connecting the dots, where the dots are the samples.
And like when you go like 8x oversampling, whatever, like that number just means how many samples between two real samples that exist, right? Like 16x oversampling is 16 samples between two real samples.
Cool. Yes. And of course, when you're doing an oversample for like sample rate conversion, like you have a project at 96 kilohertz and you want to have it at 48 kilohertz, you are not so naive as to use linear interpolation, because linear interpolation is effectively a low pass filter. You don't want that. You want more control. So you use things like sync interpolation or other things like that. But we are not going to be fancy. We are going to be simple, which is also good maybe for this effect, because you're probably not going to hear a difference, and it's much faster to compute linear interpolation. It's the fastest interpolation algorithm.
Yeah, and if it sounds a little like artificial, like that's just bonus to me.
Yeah, I guess the simplest oversampling algorithm is sample and hold, where if you want sample 3.5, you take sample 3. That's what we're doing now.
Again.
But the next step up, sample and hold, is linear interpolation.
Cool.
So that's what we're going to do next. So let's do, so we need to get the sample on the left and the sample on the right.
Cool.
Of the value that we are going for. And to do that, we first need to compute this 3.75, right? We need to see what is the sample that we want. Right now, we are computing this with buffer index times speed modulo buffer size. But modulo is an operation that in JSFX is going to give us an integer. So we already lost that information. We already have 3 instead of 3.75. We want a float. So how do you get a float out of this? How do you get the remainder as a float?
You times it by 0.00 something, like times it by something that has a decimal.
Ah, that's clever. You can do that, but the number of decimal places you're going to get is fixed.
Oh, what if we take the modulo and divide it one more time by do a normal division by the buffer size, and then add the division and the remainder. So if it's like 10 modulo 4 gives us 2, then we divide 2 by 4 and it gives us 0.5, and we add it to 2. Does that make sense?
Yes.
Yeah.
That is closer to the technique we would use, but the problem is that modulo is the remainder of the division.
But then once you have the division, once you have the modulo, you can then just do a second division. This may not be efficient. Yeah. So you get the 2, and then you divide 2 by 4 one more time. Instead of getting a modulo, just do a division and you get an integer, or you get a decimal.
Yeah, that does make sense, doesn't it? So if we had like the remainder is 3, you can just take 3 divided by buffer size. That will give you the fractional part of that. Yeah, that makes sense. That was not what I was going for, but that
maybe not super
sense.
efficient, because you're like doing the same thing to the same number a bunch of times. Probably there's a better way.
Yeah, the way that people tend to do is with that divide, take the floor, and multiply trick.
Oh, okay.
But yeah, no, your idea is smart and I like it. So that's what we're going to do. So let's, right after we collect the samples, so right after gain 1 r equals SPL1, right there, let's add a new line that maybe we can call this the read head or buffer index read or something like that.
Let's see.
Read index, maybe.
Read index I like the most, I guess.
I would probably go for buffer index read and buffer index write, whatever. So let's start.
Cool, let's do that.
Well,
what if buffer index and buffer index read? Because we already know buffer index is writing. What else can it do?
Well, besides writing, it can read. But no, this logic is not correct. Because what we want is, we are using the modulo there to get us a certain position.
Yeah.
And either I am not understanding your logic, or I think that once we get to the position, we are getting to the position like we would like to have gotten at 3.75,
Yeah.
but we are getting at 3. How do you recover this 0.75? I don't really see how that's going to work.
Yeah, okay, then let's not do it because I can't, like from a mathematical point of view, I can kind of justify. So I mean, so what I mean, right, just to use like real numbers is like 10.4 give us a modulo of 2. Then you go 2 divided by 4 and you get 0.5. And then you have a third operation where you go C equals the top number plus the fraction. You know what I mean? So A is this, and then B is this, and then C is A plus B. But this may be like a very kind of basic way of doing it, or probably is.
No, but I think you're right. Yeah, let's do it.
And actually B is A divided by, so yeah, so A is like 10 modulo X, B is A divided by X, C is A plus B.
Right.
Yeah.
Okay, so implement that.
Okay. So buffer, and we want to feed this into this, right? We're feeding it, like oversampling needs to take place before we write.
No, oversampling is going to take place after we read. We are going to read 2 samples and interpolate them.
Oh, so shouldn't this go down here?
No, because what we are doing in those 2 lines that start with SPL 0 and 1 is we are outputting some value. We are reading from the buffer and outputting what we find there.
Ah, okay. So, I mean, I'm going to try, but I may be doing, or I'm almost definitely doing something wrong. So that would be this. Fuck. Wait, just to make this easy, I'm gonna give these values a very basic name until I do the thing. That's divided by buffer size. And then the final result that we want is A plus B. And then final goes and replaces all of this. Or I guess we're still doing some steps to oversample.
No, I don't think that you want to get stuff from grain 1L right away. We are computing the indices first. So I think that you don't want to have the brackets at all there. You want to remove that part.
Okay. Like all of this, right?
Yes. But don't remove those parentheses. The parentheses, I think, are important because I think modulo is calculated first and multiplication second.
Cool. So jobs, goops, and of course zoops, and then jobs and goops. So that just gives us one number, and then we need another one of these, right?
No, but hang in there. What you wrote in the screen, I am having the hardest time reasoning about this mathematics. I don't think that what you have on the screen now is what you had on the screen before, below. I don't think you implemented the same thing you showed me before.
I did modulo, so X is buffer size. Then I did division. Then I added these two numbers.
Yeah, but you had division. B was equal to A divided by X, and that's not what you have there. You don't have A divided by X.
Oh, I see. Yeah. A.
Now that's more like A.
Okay, there we go.
Okay. So this first thing, A, that you're calling A, is the place where we want to get a sample. B is the weight we want to give to that sample in the linear interpolation. So let's give these guys names. A, let's call it like...
Wait, hold on. Maybe not. This part, the aim of this part is to get the decimal value that modulo gives as a remainder. So this whole number is one float value. So that is like the value of sample 3, and then we need a separate one to get the value of sample 4, and then we interpolate.
Yeah, okay.
I may be confusing you and like...
Yeah, so let's start with something simpler instead.
Okay.
Instead of trying to compute this decimal place, calculating the remainder of a division and just getting the decimal places out, that's such a simple thing. We can probably Google this and find out the answer. Let's reason about something else that I know the answer of and that is conceptually much simpler, which is we want samples 3 and 4, right?
Yeah.
So we already know how to compute this number 3. That's just the formula we already have.
Okay.
We just need the number 4. But we don't want to simply add 1 because we may be at the edge. So we need to wrap back. So what we want to do is maybe have a variable that reads like sample 1 left 1. I don't know. It's just we need 2 samples for the left channel, right?
Mm-hmm.
So let's call it whatever
I'll
name you come up with.
call it small sample, right? One is small sample, one is big sample.
Okay.
And then
so that is going to be right. So small sample L is what you are assigning to SPL0 right now. So take the code that is right after the equal sign and copy it there.
Big sample is this.
And then, no. Big sample is exactly the same. So paste that again. Except that we want the next one. And so we want to add 1 to the index, but we don't want to go over buffer size. We don't want to overflow. So add 1 in the parentheses. So buffer index times speed plus 1 modulo everything, modulo buffer size.
Oh, okay.
So that's just going to get the next one.
Yeah.
And put semicolons at the end of these 2 lines. So we already have small sample L and big sample L. Then SPL0, go to the line that reads SPL0. SPL0 equals, we want to compute the average, the weighted average between small sample L and big sample L.
Okay.
So you can say something like small sample L times weight, where weight is the reminder that we are so desperately trying to find, plus big sample L times 1 minus weight, where weight will be normalized. It will be between 0 and 1.
Cool.
And you can get rid of the rest of this line. Oh,
good. I like getting rid of stuff, I guess. All right. Am I missing? No, because it's, I think I'm not missing any brackets.
Now, the hardest question we have, if we can answer this question, we'll have oversampling working with linear interpolation. The hardest question we have is, how the hell do we get the fractional part of the remainder of a division? Let's Google this because I am not able to come up with the thing myself. I know that the solution has to do with multiplication, flooring, division, blah, blah, blah.
Before we look it up, remember in the ping pong delay, there was a point where we had to calculate milliseconds to samples. But for other formulas, we wanted just samples as samples. So we had 2 variables going. So can we have a similar operation where here, since we need the modulo, we use modulo, and then where we need the float value, instead of using modulo, just use division, and they are 2 different variables. One variable works to give us a whole number we can use, and one variable just gives us the float value because it's just a straight division.
Well, the float value, the problem is that the float value,
Let's just look it up.
Okay. Okay, we can either Google or we can work on this from first principles. Maybe we can try to work on this first principles. And are you saying this in all caps because you have caps label
Yeah.
or because you're
No,
English?
I'm not intentionally doing that. Get the decimal point of a modulo operator in Lua. I guess if you say EEL2, it's not gonna work. But I guess if we do Lua, it's probably gonna be a very similar thing, no?
I don't know how modulo works in Lua. You may do the modulo thing instead of just the integer modulo thing.
But if we go to the reference manual and we go modulo division, margin defines an A. Yeah, so this is just a shorthand to make the modulo happen, right?
Well, that's that thing right there. Oh man, I that thing right there is doing the division, floor, and multiplication thing. It's just that my brain is fried and I cannot make sense of it at all. But that thing is the answer. I know intuitively because I have worked out this problem many times before. But my brain is really fried right now. So the answer lies in there. I just don't know how to make sense of it.
Okay, so I'll just copy this, bring it over for ref.
So let's work on this based on first principles. So let's say that A is our buffer index times speed. So let's say that A is like 17.
Okay.
And let's say that our
buffer
size is, I want the result to be fractional, so
6,000.
No, I was thinking of a number like 9.
Okay. So that will be 8.
No.
The modulo result, like the remainder of this division, is 8.
No, that's 2, isn't it? No, it's actually 1. 1 point something.
If you do a division, I thought we're doing a modulo.
But modulo is division. It's the reminder of division.
Yeah. So 17 by 9, yeah.
Man, I am so embarrassed that I have no idea how to work this problem out because it's supposed to be so simple. But it just goes to show what happens when your brain is completely fried. So the remainder of the division between 17 and 9.
Let's do this. Okay, so this will be 2.5.
No, because that's the remainder of that is an integer. It's 5.
Oh, you want it to be a fraction. The remainder you want to be a fraction.
It needs to be, yeah. That's the problem we are working on. We don't want to land on the sample. We want to land between two samples.
Okay, I see.
Yeah, we can also do something like 5 and 3 to keep things super simple.
Let's do that.
5 and 3. The remainder of the division between 5 and 3 is 2. And if you divide 5 by 3, what is 5 divided by 3? If you just divide 5 by 3.
It is 1.66, yeah.
Yeah, so that's the number we want. We want the number 1.66. That's our goal. How do we get 1.66 out of 5 and 3? You just divide.
Yeah.
Okay. Let's go to the next number up the line here. What we had, instead of 5, we had 10.
Okay. The modulo is 1. The fraction number is 3.333.
And we want a number between 0 and 1. So we want 0.333. That's what we want. We want a number between 0 and 1. So you just take the division and subtract the modulo. That's what you do.
Take the division, subtract the modulo.
Is this right?
I feel like no.
No. No. You take the result of the division.
Yes.
And you subtract the floor of it.
The floor, that makes sense, yeah.
Yes. Okay, that's what we do. We divide the numbers, not modulo, divide the numbers. Good old division.
Yeah. Right here.
No, don't touch that. Because that's grabbing samples, and that part we know is right.
So here.
We just need to compute the weight. The weight is...
Let me just make a new line. Weight. Or sorry, let me write weight correctly before we go further. Okay, weight is big sample L.
Yeah, so let's call... No, it's not big sample L. That's a sample. We are now computing the weight. So the weight is this fraction. So we need a variable that is the result of the division. So maybe you have a variable before that is result of division.
Division result, just division. I'm just gonna call it division.
And then you take the formula buffer index times speed divided by, not modulo, buffer size.
Zoink.
It's the formula in small sample L. Oh yeah, that formula, exactly.
Zoinks.
And now weight is equal to division minus floor of division.
Division. That makes sense. Is math floor or is it just floor?
Just floor. And I don't think you have a minus there.
No, I have an equal sign. Okay, division minus floor. That makes perfect sense to me. Because like, yeah, again, plugging in numbers, this will be, let's say 10 and 3. This division will be 3.33. And then this will be 3.33 minus 3, which is 0.33.
0.33, which is guaranteed to be a number between 0 and 1. And that's the weight. That's how near we are to big sample L, or how far we are from it. So put the semicolon at the end of the line that's computing the weight, get rid of the junk right below it, and maybe let's reproduce this for the right channel. So there will be a bunch of copying and pasting.
That's fine.
Or maybe before, let's not worry about stereo, right?
Right.
Comment out the line that reads SPL1 equals something.
Let's see if I'll do it right this time.
Just...
Oh, yeah.
You can just do 2 slashes and it's going to comment the rest of the line.
Oh, I see. When it's a single line, you don't even need the fancy business.
Yeah.
Cool.
And then the line that reads SPL0, say SPL0 equals SPL1 equals that. And then we have a mono effect.
I know, it's fine by me. Cool.
Okay, mute the master.
Okay, because we are this time doing some crazy. But no, I think we're still not touching the input and output. Yeah.
Oh yeah, we are. We are computing the average of 2 samples and blah, blah, blah.
Oh, okay. Wait, is our speed operational?
It should be.
I don't hear it. I just hear it really fast.
Well, make the number smaller. Make value that works well smaller.
Yeah, let's put another Zoinkaruni here. How is this even working? I wrote it wrong. Did you see that? Oh, I think it was after compiling. Yeah.
Yeah.
Okay, now I definitely hear the speed and it's too slow, so I'll just do, I think this was okay. The thing that you said from the beginning. Oh, I like the low. It's like proper grimy stuff. Cool.
Okay. Oh man, let's get out of here.
Okay.
We did oversampling, we did slew limiting, we did pitch shifting. we worked through a code that was awesome, 5 lines of code, but kind of difficult to wrap your head around. That was fun.
Yeah, that was good. Just pitch shifting is like the best sounding thing ever. I feel like it's my only musical gimmick.
Yeah. Oh man, I was in despair when I couldn't figure out that division thing. Man, hard times.
Yeah, I think also like, so the system I was proposing was to kind of reconstruct the number, but we didn't even want that. We wanted just the decimal on its own.
Yeah.
Yeah. So, okay, so I guess, is the pitch shift portion complete and I should now bring it into the ping pong delay, or we still have some, I mean, other than like copying pasting for stereo, which I guess the ping pong delay, we made it multi-channel. It's not stereo.
Yeah. So we could have this multi-channel as well. And another thing we can do is the overlapping of the grains and the crossfading, because we are not using
we gotta do that.
grain
Yeah.
2.
Oh yeah.
We are not using grain 2.
Yeah. Let's do that.
Yeah. Okay, but not today.
Yes. Well, I haven't streamed in a while, so not a lot of people showed up, but whatever, man. I had fun. So thanks for being here. A lot of you who were here for like 30 seconds and then bounced. I know who you are and I'm coming to your houses. Thanks, Leandro. This was fun. I'm glad we're back into it. Like, website stuff is useful for me, but this is where all the fun is. So yeah, any last words?
I see you tomorrow over at my channel for the C++ digital signal processing juice study group meeting.
Yeah,
it will be a lot of fun.
Yeah, I'll have to be late. I think for every meeting I'll be like late a little bit because I finish at 2. But yeah, see you with a little bit lateness.
All right, see you tomorrow. Thanks for having me.
And everybody else, take care of yourselves. And yeah, don't do drugs, or do drugs. I don't care. Do whatever you want to do. Where is my start screen? Oh, whatever. Or my end screen. I don't know where it is, so just bye.
Professional streaming here.
Yeah, I think I loaded the wrong profile because I was doing so many testing and I duplicated